I'm Swati Verma, Assistant Professor, Chhattisgarh Swami Vivekanand Technical University, CSCTU Bhilai. Welcome you all to the course on Industrial Automation and Drive. Today, we will start with our 35th lecture of the course, which will focus on Introduction to SCADA, Architecture and its block diagram. So, let us start with the introduction of SCADA. So, first, what is a SCADA system? SCADA stands for Supervisory Control and Data Acquisition. It is a control system that uses computers, network data communications and graphical human interfaces, which is called as HMIs, to manage and control the industrial processes. The SCADA system communicate with other devices such as PLC and PID controllers to interact with the various industrial process in plants and the equipments too. The SCADA systems are very crucial in control systems engineering as they collect and analyze the real-time data from processes, record it and log this data and also display it on various graphical interfaces, which is called HMIs, the human machine interfaces. This SCADA system enables the process control operators to supervise, which stands for S in SCADA, what is happening in the distant field or what is happening inside the plant or inside the industry, even from a distant location. It also enables the operators which is sitting on its computer to control, which stands for the C in SCADA, all these distance processes by interacting with the HMI. In the SCADA system, it basically comprises of two things. First, the hardware and the software components that gather, process and present the data from remote locations. These systems are very pivotal or important in the manufacturing, energy, water treatment, transportation and many more other applications where monitoring and controlling the processes are paramount in nature. What sets a SCADA apart is its ability to gather data from the sensors and instruments in real time. It also enables the operators to make informed decisions promptly and to take the actions accordingly to that. This technology significantly optimizes the operations, also enhances the safety and overall improves the productivity in the industrial settings. The major milestones of SCADA system are: first, operating and establishing the communication with different types of sensors and actuators. Next, the operation of the single or multiple machines from the local or the remote location through the human machine interface HMI. Next milestone is to control the bunch of operations from a central room which is distant or which is situated at a far distance from the plant or the industry process. Next is to operate and control the multiple operations and acquire the data such as the vital parameters like frequency, the phase shift, the temperature, pressure, load and the demand factors. Now, we will discuss the history of the SCADA. So, earlier the controlling of the industrial plants and the manufacturing floors are done manually with the help of analog equipments and through the push-pull buttons. As the industry size is growing or the industrialization get a rapid pace, so this employ timers and relays to provide supervisory control to a very fixed level and with a minimal automation. So, with the time, a fully automated system with a more efficient system comes or becomes necessary for all the industry process and for the industrial automation. But in real, unfortunately, this relays and timers could solve the problems only with a minimal automation functionality and reconfigures the system difficult. So, a more efficient and a fully automated system was required by all the industries. Okay. So, the computers were developed for industrial control purposes in the early 1950s. With this, slowly the concept of telemetry was introduced for virtual communication and the data transmission. Around the years 1970, the term SCADA was coined and raised along with the evolution of microprocessor and the programmable logic control advancement and its concepts. This advancement in the PLC and the microprocessor allowed for more automated and reliable data acquisition and the control processes. As the year rolled by, the distributed SCADA systems were developed in early 2000s. Now the modern SCADA systems have came into the existence and allow us to control and monitor the real time data by sitting anywhere across the world. Throughout the following decades, the SCADA systems continued to evolve, which incorporates the advancement in the communication technologies, data processing and user interfaces. The integration of the internet connectivity and the cloud computing revolutionized SCADA and leads to advancement which enables the remote monitoring and control capabilities on a global scale. Now we will discuss the architecture of the SCADA system. But before discussing and before going into depth about the architecture of SCADA, we should first discuss the basics of the SCADA system. Okay. So, consider the block diagram of the SCADA system which is shown in the figure, which mainly consists of different blocks consisting of human machine interfaces HMI, supervisory system, remote terminal units RTUs, programmable logic controllers PLCs, communication infrastructure and the SCADA programming. After discussing the basics of the SCADA, we will go in detail about the architecture of SCADA and the different types of SCADA system in detail. So, the first basics of the SCADA system block is human machine interface HMI. What is HMI? It is an input output device that processes the data to be controlled by a human operator. It is used by linking to the SCADA system software programs and databases for providing the management information which includes the schedule maintenance procedure, detailed schematics, logistic information, trending and diagnostic the data for a specific sensor or a machine. This machine interface facilitates the operating personnel or human operator to see the information graphically or to detect any fault or to see the values of various important parameters going on in the industrial process. Next is the supervisory system. Supervisory system is used as a server for communicating between the equipment of SCADA system such as RTUs, PLCs, sensor actuators, etc. And the HMI software which is used in the control room workstations. The master station or the supervisory station comprises of a single personal computer in a smaller SCADA system, and in case of larger SCADA system, the supervisory system consists of distributed software applications, disaster recovery sites and the multiple servers. These multiple servers in the larger SCADA systems are configured in a hot standby formation or dual redundant which continuously controls and monitors in case of a server failure for increasing the integrity of industrial system. Next is the remote terminal units. The physical objects in the SCADA systems are interfaced with the microprocessor controlled electronic devices called as remote terminal units In short, they are called as RTUs. These terminal units are used to transmit the telemetry data to the supervisory system, and it is also used to receive the message from the master system for controlling the all linked or the connected devices. Now, this is due to this operation of these terminal units, they are also called as the remote telemetry units. Next is the programmable logic controllers, PLCs. In the SCADA system, PLCs are connected to the sensors for collecting the sensor output signals in order to convert the sensor signals into digital data format. PLCs are used instead of RTUs, which is called the remote terminal units, which we have just discussed now, because of the advantages of PLCs like the flexibility, configuration, versatility and affordability compared to the RTUs. Now, the communication infrastructure. Generally, the combination of radio and the direct wired connections is used for the SCADA systems, but in the case of large systems like the power stations and the railways, SONAT, SDH are frequently used. Among the very compact SCADA protocols which are used in a SCADA system, a few communication protocols which are standardized and recognized by SCADA vendors send the informations only when the supervisory station polls the RTUs. Next basic of SCADA unit is SCADA programming. The SCADA programming in a master or human machine interface is used for creating the maps and diagrams which will give an important situational information in case of an event failure or a process failure. The standard interfaces are used for programming the most commercial SCADA systems. The SCADA programming can be done using derived programming language or through a C language. The basic block diagram of SCADA system as shown in the figure represent the basic architecture of the SCADA. The SCADA, which stands for Supervisory Control and Data Acquisition System, are different from the distributed control system that are commonly found in the plant sites. When distributed control systems cover the plant site, the SCADA system covers much larger geographic area. The above figure depicts an integrated SCADA architecture which supports the TCP IP and UDP and the other IP based communication protocols as well as the industrial protocols like the Modbus TCP, Modbus over the TCP or Modbus over the UDP. This all work over the cellular, private radio or the satellite networks. In the complex SCADA architecture, there are variety of wired and wireless media and protocols which are involved in getting data back or transmitting the data back to the monitoring site. This allows the implementation of powerful IP based SCADA networks over the landline, missed cellular and the satellite systems. The SCADA communications can utilize a diverse range of wired and the wireless media. The choice of the existing communication depends on the characterization of a number of factors. The factors which control the choice of existing communication are basically the remoteness, second the available communications at the remote sites, next the existing communication infrastructure, next the polling frequency and the data rates. These factors impact the final decision for the SCADA architecture. Therefore, a review of SCADA systems evolution allow us to better understand many security concerns. Now comes the types of SCADA system architecture. In industrial automation, when you use the various devices at the physical level, it is necessary to understand the architecture designed in them. The devices which communicate with each other in many number of ways, either through hardware or through the communication to share the data between the field and the control room. Which link goes in which connection is very important to define and the work out. So, once we understand the architecture, then we can easily work in the system. So, understanding the architecture of SCADA system is essential when designing it, as it is one of the fundamental component of the automation. The SCADA application typically runs on a server, and the clients like the desktop computers and the screens are then function as human machine interfaces HMIs by connecting them to the server. Since the operational devices which we have discussed like the PLCs, the programmable logical units and the RTUs are also connected to the server, we can now use the SCADA clients to control and monitor the all operations. So, in this we will learn the various types of SCADA system architecture such as monolithic, distributed networks and the Internet of Things. So, there depending upon the SCADA architecture we can define in the 4 different generations. So, based on that we have 4 SCADA system based on the architecture. First generation is the monolithic or also known as the early SCADA system. Second generation is the distributed SCADA system. Third is the third generation network SCADA system, and last is the fourth generation which includes Internet of Things technology SCADA systems. Now we will first discuss about the monolithic the early SCADA system, which is also called as the first generation SCADA system. As you see in the diagram, the mini computers are used earlier for computing the SCADA system, but in the earlier time during the time of first generation, the monolithic SCADA systems were developed where the common network services were not available. Hence, this monolithic or the early early SCADA systems are independent systems without having any connectivity to the other devices. As you can clearly see in the diagram, the monolithic SCADA architecture consists of single SCADA system communicating with the various RTUs or the remote terminal units. The RTUs, the remote terminal units, are also a type of PLC, but it does not have its own display and it communicates majorly through the wireless protocol. Also, it is used in remote locations in a factory where the environment is hazardous and access is not possible, and placing or the presence of human personnel is not recommended. So, here the WAN or the wide area network and the LAN, which stands for the local area network. The WAN, the wide area network, can be best understood with an example of the internet we are using nowadays. We have to use some kind of network, the wired or wireless, to connect these systems together to transfer the data between the RTUs units easily. All the RTU units, the remote terminal unit sites, would connect to a backup mainframe system for achieving the first generation data system redundancy, which was caused in case of failure of the primary mainframe system. The functions of the monolithic SCADA system in the early first generation were only limited to monitoring the sensors in the systems and flagging any operations in case of surpassing the program alarm level, or whenever a certain values passes the threshold value, in that case it flags any operations. Basically, it will connect the various devices irrespective of their location together. As we have seen in the figure, only one SCADA system is the master and it cannot communicate with the other SCADA system. So, basically this is a simple stand-alone system. We cannot mix another type of data in this network or in this SCADA architecture. The connectivity with the SCADA master station was very limited by the system provider in this first generation SCADA architecture. The connections to the master were usually made at the bus level through a patented adapter or a controller connected to the backplane of the central processing unit. So, next is the distributed SCADA system. The distributed SCADA system or the second generation SCADA architecture is the advanced version of monolithic architecture. As compared to the first system where a single SCADA system was used and was not able to communicate with the other SCADA system, in this system multiple stations can communicate or can be linked with each other. You can refer the figure which you can see it is an extension of the previous version of the SCADA architecture. Here the single SCADA PC is now connected to a LAN or the local area network. On this network you can see the other SCADA systems are also connected. So, now in this second architecture the data sharing between them is not possible. Either it can be client systems or have some other server systems. With this architecture the redundancy is also possible. Only one single LAN network is available, in that you can integrate your system easily. The distribution of the individual functions of the SCADA system in multiple systems provided more processing power for the system as a whole than would have been available in a single processor system. But the networks that connected these individual systems were generally based on the LAN protocols and could not reach beyond the limits of the local environment. In the second generation distributed SCADA architecture, the sharing of the control functions is distributed across the multiple systems which are connected to each other using a local area network. Hence, these are termed as distributed SCADA systems. These individual stations are then used to share the real time information and the data and the command processing for performing the control task to trip the alarm levels of possible programs. Here the cost and size of the station were reduced compared to the first generation system, as each system of the second generation was responsible for performing a particular task with the reduced size and cost. But even in the second generation system, the network protocols were not standardized. The security of the SCADA installation was determined by a very few people beyond the developers, as the protocols were proprietary. Also, the security of the SCADA system was ignored. So, now third architecture comes, which is called the third generation SCADA architecture, known as network SCADA system. The current SCADA systems are generally networked and communicate using wide area network system over the data lines or a phone system. These systems use the Ethernet or the fiber optics connection for transmitting the data between the nodes frequently. This third generation SCADA systems uses programmable logic controllers for monitoring and adjusting the routine flagging operators only in the case of major decision requirement. Network SCADA architecture is the current crop of architecture we mostly use today in almost all the big industries. In a distributed system, you saw that only a single LAN network was available. If you had your system outside this network, then you would not be able to communicate with it. Okay? So, to evaluate this limitation of the distributed system architecture, the network architecture was developed. In this system, outside a network can communicate with each other through a wide area network or also through an optical fiber communication medium. Through this, a SCADA system fitting in some remote part of other countries can also get access to the system and can also communicate the data transfer with it. This means that the SCADA system could now not only be used in a single plant, but throughout the several plants with the physical locations far or very far distant from each other. With this network architecture, the data and the supervisory can be accessed anywhere, even from a physical location different than the plants. The main improvement in the third generation is to open the architecture of the system using standards and the open protocols, which enables the distribution of SCADA functionality through a wide area network and not just limited to the LAN. The first and second generation SCADA systems which we have discussed are limited to the single site network or to a single building, which are generally called as the sealed systems. These systems cannot have any risk compared to the third generation SCADA systems, which are now connected to the Ethernet or the internet, causing the security risk. So, there will be several parallel working distributed SCADA systems under a single supervisor in a network architecture. Now comes the fourth generation SCADA architecture, the Internet of Things. In this fourth generation SCADA architecture, the infrastructure cost of the SCADA system is reduced by adopting the Internet of Things technology with the commercially available cloud computing application. The maintenance and integration is also very easy for the fourth generation as compared to the other earlier SCADA systems. This fourth generation SCADA system architecture are able to report the state in real time by using the horizontal scale from the cloud computing facility, and thus more complex control algorithms can be implemented, which are practically sufficient to implement on the traditional PLC network. However, the security risk in case of decentralized SCADA implementation, such as heterogeneous mix of proprietary network protocols, can be surpassed using the open network protocols such as TLS inherent in the Internet of Things, which will provide the comprehensible and manageable the security boundary. Now we will discuss in detail about the SCADA architecture block diagram. In the figure of the SCADA architecture block diagram, you can see there are so many devices and systems. So, we can divide the whole systems into the 5 levels to understand the working of each part of the SCADA systems. Now, the first level, which includes sensors and actuators. So, firstly, all the ground level or the 0 level devices that actually communicate with the physical environment comes under this level. So, there are the many different types of sensors and actuators, all the physical devices, all these types comes under the level 0. Now, you know the sensor and actuators are the devices that can sense the physical temperature signal like temperature, light, moisture, etc., and convert into an electrical and the electronic signals. While the actuator is a device that makes an electrical or electronic signal to physical or the mechanical signal. For example, if you want to control the flow of a liquid using an electrical method, we can use a control valve actuator. We can also use the flow sensor, the pressure sensors, the LDR and many more sensors in the SCADA systems. So, this SCADA sensors and actuators comes under the level 0. Now, the level 1, which is called as the programming devices. Under this, the programmable logical controllers and the remote terminal units, all this comes in this level 1. Suppose you are at leader of your team, then your workers and the co-workers have to obey your instructions. Similarly, the programmable devices directly control the ground level devices or the physical devices such as sensors and actuators connecting through a LAN and the WAN network. The SCADA system established with only the LAN or the local area network or through combination of both the LAN or the local area network or the wide area network. But here I mentioned in the figure you can see I have mentioned the two programmable devices. One is PLC and other is RTU. In this system, the PLC exists to establish the communication with LAN. On the other hand, the RTU can assist to establish the communication with WAN. So that you can realize the system more clearly, I have mentioned both PLCs and RTUs in the figure. Level 2 is the local control and the HMI. Generally, the computers are connected with the programmable devices belong to this level. We all know that our brain or the neurological signal controls our all physical activities. So, in this case, all the devices are instructed or commanded by the software installed in these computers. The operators operate the computers and get instructed by this local control and the HMI. Level 3 is the coordination. In this level, the computers come to a coordination system. Generally, these computers are connected to the multiple plants or the industries, so it can help to gather the data from different plants or from one place. Level 4 is the central control. This is the important and the crucial level for the SCADA system. We can take a decision finally after analyzing by brain or by analyzing the data. In this case, this level is for decision making after analyzing all kinds of acquired data. So, that is all for this lecture. In this lecture, we have covered the SCADA fundamentals, in which we have discussed the basic architecture of the SCADA, the basics of the SCADA units, and we have also discussed the application of the SCADA. So, that is all for today. In the next session, we will discuss how we can make the interfacing of SCADA with our PLC. So, thank you. Happy learning.